Hi there. Today what I want to talk about is some of the real-world aspects of sampling a signal. We've talked about ideal effects in the frequency domain and the time domain, but but in the real world we have to make a few more adjustments. And I've got some notes here. I've just copied them and I'll make them available, and I just flash them up here and we'll just sort of visit about them. They're pretty simple concepts. One is quantization. Um, in an ideal analog to digital converter, we just take whatever this value is. This is the value of the signal at the nth time interval, and we take its value and we assign it into x of n. Okay, but in practice, that's a little bit harder to do than it looks like at first glance, because this x is actually ends up being stored on a computer or a microcontroller or in RAM. And RAM memory is electronic memory that has a finite number of bits, and we're going to say B is the number of bits. So typically there's 8 bits or 16 bits, 24 bits, 32 bits, that kind of thing. For example, if B is 8, then we have to represent some number that, like x, it might actually be, it can be anything, 97.32975, can be anything, but we may have to compromise, and that by the way is x sub q. Okay, we might have to truncate a whole bunch of that stuff to put it inside computer memory. And the reason for that is that we only have, like if b is equal to 8, we only have 2 to the 8th possible values that we can use to represent all infinity of possible input voltages. Okay, so we got some compromising to do. And the way we do that is it's called quantization. Okay, so we throw out some detail and keep the most important part. So that's called the quantized value. The error, the difference between the actual value and the quantized value in this case is all of this stuff right there. That's the error, quantizer error, or quantization error, or quantization noise it's also called. So it's called those different things. Alright, let's look at a simple 2-bit analog to digital converter. There aren't very many of these around because this is for illustration purposes that I'm talking about. But basically, we see the input signal that I want to quantize right there. This is voltage at the input to the analog to digital converter, and this is time going this way. So every capital T seconds, the sampling interval is t, we're going to sample this nice smooth signal and assign it to one of these memory locations. We're only going to use 2 bits to represent each sample, however, and those 2-bit assignments are shown on this axis. This axis shows volts, and correspondingly over here we show the 2-bit words used for each sample. So you see what's going to happen. We only have 4 possible, 2 to the 2 is 4, 4 possible voltage levels, and at each sample interval we're going to assign the signal to the nearest quantized voltage level. So at this first sample interval, the voltage is here, we're going to assign it to that one. The next sample interval, we're going to assign the voltage to that level, again, the 0, 0 level. And then here, the next sample interval, the actual voltage is here, we're going to assign it to that. Okay, so this voltage is assigned to this voltage level, this voltage is assigned to that voltage level, and this voltage is assigned to that voltage level. So you can see what kind of price we're paying for being able to put this on a digital computer. Alright, so at each sample interval we assign the continuous voltage to the closest quantizer value. And the output is a stream of sample words, 0, 0 for this one, 0, 0 for this one, 1, 0 for this one, and 1, 1, 1, 1 for those 2 samples. So those are the digitized results of this whole thing. The quantizer error, and you see I've rewritten it a little bit differently. I put the quantized value minus the actual value. It shows up differently in different books. But that's the error. It doesn't really matter which way we put it. This error has all the properties of added noise, and to show that, I'm going to rewrite this. X, the quantized x, is equal to the original x plus the error. So it looks like added noise. E is kind of a random thing, sometimes high, sometimes low. Okay, while I've got this figure on here, I wanted to point out something. The quantizer step size is this voltage difference between each level, and we're going to call that delta. So that's the quantizer step size, and I think it's clear that the biggest error, the maximum value of the error, is well, let's take the absolute value. The maximum magnitude of the error is delta over 2, because if the error is any bigger, why the thing, if it was operating properly, would assign it to like if we had, there's delta over 2, we would always assign it to the closest interval, so we would never have anything larger than delta over 2 for the error. Okay, I switched pages on you. What we can do with this kind of model, where the quantizer error is modeled as noise, we can analyze it kind of probabilistically. This is something we do in EE 4220, which you haven't had yet. So if I can draw a line there, okay, yeah. But you can find the average power in that error signal, and it turns out that's what that's supposed to represent, P sub Q, the average quantization error power. Since it's a signal, it has power in watts, and it's delta squared. Remember, delta is the step size, delta squared over 12. And that assumes that the signal that we're quantizing is a sine wave. Alright, but this is a useful result. And sine waves are kind of like other signals, speech or music or whatever. The average signal power in a sine wave, there's the time average. You take 1 over t, you take the signal squared, and you integrate that, and you get the time average. This is a well-known result that you probably know, that the result is x squared over 2, where x sub m is the magnitude of the sine wave. So now we've got signal power and we've got noise power. A very, very useful thing to do is to take the ratio of those. It's called the signal to noise ratio, and since our noise is due to quantization, this is the signal to quantization noise ratio, SQNR. Quite often people just say SNR, okay, but for this particular case we're going to refer to it as SQNR. And if you take the ratio of the signal power to the noise power and work the algebra, you get 6x squared over delta squared. We can get a little further with this. If you remember that the maximum and minimum voltage range at the input to the quantizer, Vmax minus Vmin, that's the peak to peak voltage. If we divide it by the total number of levels that we have, that gets us this step size value in volts. Okay, and so if we plug delta that we just got into there, we now have and do some simplification, we get a result for the signal quantization noise ratio is 3/2 2 to the 2b. If you can read that, 3/2 2 to the 2b. And if we take 10 log of that, log base 10, we get the signal quantization noise ratio in decibels. And it turns out that this is the result. Signal noise ratio is 6.02 times the number of bits plus 1.76. Okay, this is a very, very important equation. Again, it assumes the input signal is a sine wave. If it's speech or telemetry or something, this constant here changes a little bit. but 6.02b is the signal quantization noise ratio in terms of the number of bits in the analog to digital converter. Okay, so the most important part of this is this 6. You don't even have to remember the 6.02 part, just remember 6. The signal noise ratio is 6b plus 1.76. Okay, so there's about 6 dB worth of improvement every time you add a bit to the signal to the analog to digital converter. Classic example. Suppose we have a CD player. They have a 16-bit analog to digital converter. So the signal noise ratio, signal quantization noise ratio in decibels, 6.02 times 16 plus 1.76 is 98 dB. In a minute we'll talk about what that means, but that's a big number. That's a lot of decibels.